Okay, let's try this again. I started a video and flubbed it badly, so hopefully I can do better with this one. So we're going to be looking at the next section, 2.6, and this is going to be looking at taking functions and putting them together, either combinations where we use mathematical operations, addition, subtraction, multiplication, or division, or putting functions together via the composite, which is something that we'll take a look at. But before we get into those, we're going to take a look at this idea of domain again. And remember, we looked at domain earlier, and we said that domain has to do with X. So the domain is all about the X values. And as this says here, the domain is the largest set. So it's going to be the biggest pool, or the ocean, if you will, of values for X that we can pull from to put into our function and have the value of the function be a real number. So if we pull an X and we put it in our function, we want the number, the output of our function, to be a real number, not an imaginary number. So this domain is going to be the biggest set of X values that will work for our function. And we already looked at this idea of domain by looking at the graphs of functions. And looking at the graphs, we determined all the values of X, the smallest value of X to the largest value of X that would be reasonable for that particular function, the graph of that function. Now we're going to look at this based just on, not the graph, of course you could graph these, but looking at and recognizing the functions. So starting out, for many functions, I dare say most functions, the domain is going to be all real numbers. So the domain is going to be this negative infinity to positive infinity for many, many functions. All values of X are reasonable to put into the function and get a real number as the output. There's going to be a number of cases where we're going to have to exclude or kick values out of the domain. And the two ones we're going to look at now are when we have fractions and when we have any square roots or even roots. Because for those functions, there are going to be values of X we can't include. We got to kick out because they're going to cause a problem when we look at them in terms of the function. So going back here, for any fractions, for any rational functions, any X values that are going to cause a zero in the denominator, we have to include. So if there's an X, if we have a fraction, we have to take a look at that denominator. Any value for X that's going to cause a zero in the denominator, we have to kick out or exclude from our domain. The other area that we're going to have to be taking a look at to see if anything has to be kicked out or excluded for the domain are square roots or any even root, because we know we can't have a negative number under a square root or an even root, because that gives us an imaginary number. And not that imaginary numbers are inherently evil, but for our purposes, we want the output of our function to be a real number, and imaginary numbers don't fall into that category. So let's take a look here at some examples. The first example we have here, f of x is equal to x squared plus 3x minus 17. Well, there's no fraction, there's no denominator, there's no square root, even root. So there's no reason to kick anything out of the domain. So the domain is going to be negative infinity to positive infinity. Nothing to kick out. If we look at this, x squared plus 3x minus 17, we might remember that this is going to be a parabola. I don't know how this is going to graph. I'm just going to roughly graph it, something like this. I have no idea what this looks like. I'm just sketching in a parabola here. But x, y, you could see from the graph our x goes to negative infinity and positive infinity. Nothing to exclude, and that would be our domain. Next example here, we do have a denominator. So we're going to have to take a look at is it possible to have values for x that are going to create a 0 in our denominator? So let's take our denominator, x squared minus 49, and set it equal to 0. Exactly what we don't want to happen, but in order to find the offenders that are going to create the 0, that's exactly what we have to do, set it equal to 0. Every semester I have students that look and say, wait a minute, what are you doing there? You told us we don't want values to be 0, and here you're exactly setting it equal to 0. Yes, I am doing what we're saying we're not supposed to do, but that's the math we have to go through, as I said, to find those values. So there's a few methods you could use to solve this. I am going to factor x plus 7, x minus 7 equals 0. So here I have x plus 7 equals 0, x minus 7 equals 0. Set each factor equal to 0 to solve. So we get x equals negative 7 and x equals 7. These are the values that when we go back and substitute into our denominator would create zeros. So I'm going to put this little not equal sign there saying x can't be those values. Now to write this in interval notation, I start at negative infinity. And now when I get to negative 7, I have to stop because negative 7 is not included. Now I can continue negative 7. Everything in between is good to go. I get to 7, and again I have to stop because notice the parentheses, 7 is not included. And then I can finish up going from 7 to positive infinity. So here we go from our negative infinity to positive infinity, but to show we are kicking out negative 7 and positive 7, I have to write my interval notation like this, very involved. Next example here is a square root. So we've looked at, no problem, negative infinity to positive infinity for our domain. We've looked at where we have a denominator and we did have a problem of two values being kicked out. Now, the second kind of function where we might have to exclude from our domain. Square roots. This, what's underneath this square root here, this has to be greater than or equal to 0. It can be equal to 0 because we can take the square root of 0. The square root of 0 is 0. So the way I write this is 9x minus 27 is greater than or equal to 0. So you see for each situation, I create a statement. Here is an equation, it's an inequality, and then we solve to find the domain. So let's go here. We can add 27 to both sides. And 9x is greater than or equal to 27. Divide both sides by 9, and we get x is greater than or equal to 3. So in order to not have any negative numbers under this square root, we can only include values of x that are equal to 3 or bigger than 3. And again, to write this in interval notation, we write 3 to infinity, okay? If we were to graph this, we would have, remember our square root function looks like that arm going. So here, 1, 2, 3, again, this is a very rough graph, but our square root function would be in this area of our graph, where we would start at 3 and go to positive infinity. So you can see there's nothing back here. So none of these values less than 3 here would be included in our domain. Okay, 2 more examples. Here we have the function f of x is equal to, and this time it's the cube root of x. So we set up here, it's square roots and even roots that could be problematic in terms of what's in the domain. Cube roots doesn't fall into that category. So the domain of cube or any odd root is going to be negative infinity to positive infinity. And again, let's consider the graph of this. The graph, you should recall, from your work in transformations, here's the mother function for the cube root. Looks like this snake slithering along here. And the domain, x goes indefinitely in the negative direction and the positive direction, so negative infinity to positive infinity. Last example here is a fraction. And not only is it a fraction, but heaven help us, it's a complex fraction. So we have the numerator of 5. Let me write this again here. So we have 5 in the numerator, and then math students' worst nightmare, in our fraction, in our denominator, we have another fraction. So this is called a complex fraction. We know when we have a denominator in our function, we have to consider, are there values of x that could be problematic, that we will have to kick out? So let's take a look at this. And when we have complex fractions, what I'm going to suggest to you is that we always clean them up some. So here, we have 5 over 1, 4 over x, and here -1. So we can see, we could put this over 1 and this over 1 just to make everything a fraction. The denominator we want to clear here is this x. We want to clean up this denominator so that we don't have this little fraction in it. So to do that, we're going to multiply by x over x, because remember, x over x is just 1. We're not changing the fraction, we're just multiplying the numerator and denominator by the same. So this gets multiplied by the x, and then this term gets multiplied by the x, and this term gets multiplied by the x. So what do we end up having here? 5 times x is 5x. I'll write this out down here just so you can see how this is going to clean up. But so here, and here we have the x. Let me put in the 1, just in case you haven't seen this. A reminder how to do complex fractions. So x times 5 is the 5x here in the denominator. X times the 4x. These cancel, which is what we want. Because we want the denominator. We're still going to have a denominator, but we don't want another fraction in that denominator. So 5x. So now here, multiplying 4 over x by x, the x's cancel, and we just have the 4. And now x times 1 is the x. So we still have a fraction, but now we don't have a fraction within a fraction. Let's take a look now, because remember the purpose of this is looking to see what has to be excluded from the domain. So let's start here. We have obviously this denominator. So 4 minus x equals 0. Here, let's add x to both sides, and we have 4 equals x. Be nice if I kept on the screen for you, okay? 4 cannot be equal to x, so 4 has to be kicked out of our domain. This looks like a y here. 4. So 4 has to be kicked out of our domain because we see 4 minus 4 would create a 0 in the denominator. Now, when we cleaned up our fraction, it looked like that, but we can't forget, going back to our original statement, we have this 4 over x that we have to consider. We have to consider the original statement. So for 4 over x, when we look at this, we can see here x equals 0. X can't be equal to 0. So we have two values that we have to kick out of the domain. 0 from the original statement that we had, and then the 4 that we get after we simplify this complex fraction. Some of you might be saying, well, what if you didn't clean up and simplify the fraction? Then you wouldn't have to worry about this 4. Yes, we would, because we would have had to take this statement, this whole denominator here, 4x minus 1, make that into an equation to solve to get our second number to be kicked out, to get that 4. I think this is the easier method, is to simplify your complex fraction and get the value there. So just to finish this up, our integral notation, we would go from negative infinity, we would stop at 0, which needs to be kicked out. Then we would go from 0 to 4, stop at the 4 because that's excluded, and then finally the 4 to positive infinity.